Hi, my name is Nathan Rutman. I'm a storage architect with HPE. Going to talk today about data management and HSM with Lustre and the Externalized coordinator. The way Lustre HSM works today is that a user issues an HSM command from a Lustre client that goes to the MDS. There's a thread in the MDS that stores those requests on what's called an internal coordinator queue. That queue then is processed to hand out individual work items to data movers that are registered with the MDS. So the data movers in the middle of the screen here register with the MDS. The MDS then hands off different work items to the data movers as they come in and as the data movers complete their activity. Data movers, in this case for HSM archiving, move the data from OSTs to some kind of cold storage archive system. But that's not all. What happens most of the time, really, is that users don't actually issue those commands, but really there's some kind of policy engine. Many of you are familiar with Robinhood. Robinhood is a policy engine, and that is the piece that actually truly integrates, issues these commands, and it can issue directly against LFS, or it can call LAPI equivalent commands, but those are the ones that actually get issued to Lustre that then go to the MDS and that then get transferred out back to the data movers. So the reality is that those are automated requests, and so those automated requests tend to happen a lot more frequently than the individual requests. So really, we're actually putting a decent amount of a decent number of requests into the MDS from this policy engine. This happens again automatically with policy, so kind of day in, day out, etc. There's another piece now that comes from Lustre where the policy engine has to kind of figure out what it is that it needs to work on. So the policy engine reads basically the Lustre namespace, ingests it somehow, and then uses that to inform its policy decisions. So now let's talk about tiering. And by tiering, in this context, I mean moving data between two different pools within Lustre. So for example, we might have a flash pool and a disk pool, and we will use our Lustre migrate and mirror commands to make those data movements happen. Today, migrate and mirror are executed in a single thread on a single Lustre client. But wouldn't it be nice if we could use our parallelized fancy data movers that are already doing our massive data movements off to our archive, and use those same data movers to do the movements between pools as well? So we've done that. We've added a migrate-HSM and an LFS mirror-HSM commands, and now we can issue those commands to our MDS coordinator, and it now will forward those on to the data movers to do those data movements as well. But really, when we're talking about tiers, we're talking about workflows, because what we generally want to happen is when a job starts, we want to move data, for example, from that disk pool to the flash, stage in the data, and when the job ends, we want to stage out that data, the results from the flash pool back to the disk. So now we have our workload manager also issuing commands to our metadata server. And hey, as long as we're at it, why can't we move data between two different Lustre file systems, right? So now we have our workload manager and our policy engine and our users sending requests for data movement to two different file systems. Both of those file systems should use the same set of data movers, but our poor little MDS brain explodes at this point.
Lustre is part of a bigger storage world. Sites might have policies for tier usage. There may be multiple file systems involved. Some of those file systems may not even be Lustre. The workload manager or users or administrators might have some policies that want to drive data movement. There needs to be data movers that move data between tiers, or maybe between other file systems. Maybe those data movers should be able to be scaled up or down depending on data movement requirements. And the question is, does it actually make sense for Lustre to be in charge of the orchestration and movement of data between all these different pieces? So what do? We move that coordinator role outside of Lustre. This is what we're talking about when we say externalized coordinator. Take that coordinator piece, makes it external to Lustre itself. So what that means is that all these requests now go to our external brain. Policy engine sends requests to our external brain. The workload manager sends requests to our external brain. Individual users, Lustre users, send requests to our individual brain. How do Lustre users do that? We add a new piece, little piece to the MDS called basically an emitter. Instead of storing the requests, instead of the MDS storing the requests as they come in from Lustre clients in its own internal queue, we just pipe those requests up out of Lustre into user space using kind of the Lustre's traditional upcall mechanisms. And then we can do whatever we want with those requests. We can, for example, send them off to our external brain. So that's what this little emitter piece does. All the explicit Lustre movement commands, like archive and restore and now migrate and mirror, all go out from Lustre clients to the MDS through the upcall to the emitter out to our external brain. The implicit restore request, same thing. So that happens to be generated by the MDS rather than individual users, but the MDS just does the same thing with it. It just sends it out through the upcall. Looks like a normal request coming to our external brain. So the brain has no further involvement with Lustre. In fact, the brain doesn't actually need to have Lustre mounted at all. It receives requests through, for example, some kind of API. It manages and manipulates these requests, prioritizes the requests, and it manages data movers by itself. It choose how many data movers to use, and forwards on these requests at its own prioritization scheme to the data movers. Data movers and the copy tools, I guess, running on the data movers don't need to register directly with Lustre. They just do whatever the brain told them to do. And when they're done, they just tell Lustre that there's been a layout change, for example. So we just do that with an LLAPI call once the data mover has finished doing its thing. So you copy data to a temp file, for example, with a new layout, do an atomic layout swap at the end, and that's it. You don't need to involve a Lustre coordinator. You just need to tell the MDS the layout has been changed, has been swapped. So we don't need to have this continuous communication now between the data movers and the MDS. Each copy tool telling the MDS what it's working on, what it started, what its progress is. The MDS doesn't need to keep track of this, doesn't need to update the logs about it, any of this. If we're interested in the status or completion or canceling or ETA of any request, we just ask our external brain, who's the guy that's actually in charge of all this stuff. So this has a bunch of advantages, I think, over the existing systems. First is it lets you prioritize your requests as you will, so you can have some sophisticated prioritization based on whatever, tokens or whatever you want. You can have your explicit commands at a higher priority than your policy commands, or workload manager might be higher priority. You can reorganize requests once they're in your brain to whatever ordering you want to. You can expire those requests, for example, if you decide that you're not interested in requests that are older than, whatever, a day because your system's overloaded. You can just expire them. And you don't need to bother Lustre with any of those details. Also, you get now, you can provide scalable interfaces for your requesters, like a policy engine that dumps a bunch of requests or a bunch of files for kind of a common activity, or the workload manager. You can provide scalable interfaces to operate on bulk movements of files. You can reuse your data movers for all types of data movement. All right, so not just archive restore, not just mirror and migrate, but copying data between file systems, whatever the capabilities of your data movers are able to do. And then finally, and maybe most importantly, you get to increase some aspects of scalability. So we can improve the scalability of the request queue itself. As I said, we can have multiple queues. We can prioritize within those queues. We can choose to discard items that are old. So that all of this leads to easier manipulation of these queues, which leads to greater scalability. And you can improve the scalability of the data movers as well, without them having to interact directly with Lustre. That means that you remove one component of scaling the amount of data movement that you can do. So you can also, with reduced interaction between the data movers and Lustre, you again decrease the RPC count and increase the potential scalability of the number of data movers that you can use. So we've submitted all these changes upstream to the Lustre repositories at WAMCloud as LU10968 and friends. That is the externalized coordinator itself, the migrate via LFS, mirror via LFS, the non-registration of the data movers, copy tools. These have all been pushed upstream. Some of them landed, some of them have not. But the code's all there, and we've actually used that code now to implement what we call a cluster store data services, a new set of services from HPE that provide this external brain. It's a set of services that are outside of Lustre, so they exist in their own little cluster as a set of independent services, so we can pick and choose from which of these services we use. But they also can operate in concert then to provide automatic data movement and tier maintenance for a multi-tier file system. It's a centralized facility, so it takes in requests from everywhere. It takes requests from Lustre users, as well as from policy engine or from workload manager. It provides an open API to request those data movements. It keeps track of them, it prioritizes them, it sends them off to the data movers. It's in charge, the data movers are in charge of their own lives. They don't need to register with Lustre. They do data movement and just tell Lustre what the results are. So the first of these pieces is the indexing service. The indexing service generates and maintains a set of databases that databases of the metadata in the file system that it keeps current. These are searchable with the administrator tool, and they're used also, the same same search and indexes are used by the policy engine to generate file sets for automated data movement. One of the goals of CDS was to achieve a high scalability, and so we are avoiding the use of a monolithic external database, and instead we use kind of a file per process model where we have lots of threads that are generating lots of database shards in parallel that reflect different portions of the file system namespace. Those shards are actually stored in the file system itself. Again, the file system is going to scale with the size of your file system, obviously, and therefore the capacity of the file system to store the databases scales in the same way. So we don't need to have big external storage just to store the database that reflects the data, the metadata in the Lustre file system. These are sequentially written, these shards. We don't use change logs, so we can avoid the random write issue. So we just re-index stale directories, and we find the stale directories quickly by looking at directory m times. And in that way, we don't have to go do kind of random seeky writes in these databases, so we can write them very quickly. So once we have this rapid search service, we can use it to answer user search queries, but also to answer automated queries. So the CDS policy engine can run periodic or trigger-based queries for sets of files matching arbitrary metadata criteria, and then generate data movement requests for those files. So we migrate them, mirror them, copy them to another file system, delete them, etc. This group will be happy to hear that we use a familiar syntax. We have implemented our policy engine based on the Robinhood syntax as well. Today, we have time-based or capacity-based triggers, but we have a set of other interesting triggers on our roadmap. When triggered, say by a flash pool reaching some threshold % full, we can trigger a rule. The rule might be to migrate files that are in the flash pool and are larger than 10 megabytes and are older than 5 days, and migrate all those files to the disk pool. Or a more complex policy that kind of treats the flash pool as a write-back cache. So we could mirror any flash file larger than a megabyte with an M time over an hour to the disk pool. This would keep the disk copy relatively up to date with the flash pool, but allow any application still using the file to read and write the flash copy of it, so it remains fast. And then we layer in a second capacity-based policy that if the flash tier exceeds 85% full, for example, we should start to punch the flash mirror copy for any files who have an up-to-date disk mirror. That means we can more or less instantly reclaim some flash space without having to wait for a file to be migrated. We just punch the flash copy and just use the disk copy from then on. And since we've kind of aggressively been mirroring flash disk, we have that the disk file pretty much up to date. So we also don't punch any more than we have to. So we allow the files to remain in flash, retain their flash mirror for as long as possible. One other fun thing about the policy definitions, they are actually just stored as plain text files in your Lustre file system. So set POSIX permissions to access the policy directory, use git revision control, whatever you want to do. So, all right, now we have requests generated by policy or manually by administrator or by a user coming through the emitter in Lustre or by our workload manager. These all come through an open API to the tiering engine. The tiering engine, which is kind of a scheduler for these requests. It keeps track of who submitted what and when, prioritizes the various requests, expires them if need be, distributes them to the data movers, and tracks their progress. Finally, we have our scale-out data mover software based on the Craig Connector HSM archiving software. It can chunk big files across nodes and restart where it left off in case of interruption. We've taught it some new tricks for the migrate and mirror tiering operations, so it can do those as well now. And it just lets Lustre know when it is starting and finishing data movement by issuing ioctls on the files itself. So no special registered copy tool protocol to worry about anymore. So there you have it. Lustre is no longer the single-tier uniform performance file system it was when HSM feature was first envisioned and implemented. Systems today need flash for performance and disk for capacity, but it sure is nice to have it all in a single namespace. And although Lustre has added features like pools and mirrors and progressive file layouts to help enable and use these performance tiers, until now there really hasn't been a way to automatically and efficiently move data between tiers. So we've refactored a bit the roles of Lustre and external tools. Lustre sticks to what it does best, which is fast I/O, and we relegate the broader data management role to a dedicated external orchestrator. We get a nice simplification of Lustre code and ongoing HSM support tickets. We get to expand the usage of the Lustre HSM mechanisms to request data movements in general, so archive as well as mirror and migrate. We add capabilities for more complex orchestration outside of tricky kernel code, right? So we don't have to put all this stuff inside the kernel anymore. And we get improved scalability in managing and servicing the data movement requests. So where does all that leave us? Hopefully, a much more capable next generation implementation of tiering and HSM data management for Lustre in a more, designed for a more complex real world multi-tier HPC environment that exists today. Thank you all for your time and attention. I hope it's been interesting and informative. I really hope to see you all again in person next year. Thanks.